Hello everybody, this is your professor at TVE course, Alex Voss, and we're bringing our first class on Faraday's law of induction. Basically, we're talking about how magnets produce electricity. Magnetic fields and electric fields or electricity interact, and they're related. And Faraday brought his law forward that showed that. Whenever we have electrons in motion, they have a magnetic field around them. Whenever a magnetic field is in motion and it goes by a conductor, it will cause electrons to move. This interaction is the basis of generators, motors, and many other types of electrical devices. And I have a great public domain film produced by the U.S. Air Force that talks about this relationship, and it does an excellent job of expanding on Faraday's law. And so let's go to the film now. Hope you enjoy it and learn a lot from it. Thank you.
This represents a neutral atom in electrical balance. Earlier, we saw how an outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of a magnet. It was proved with iron filings that a magnet has magnetic lines of force which connect its poles. For simplicity, let's consider the effect of this magnetic field on a single electrically neutral atom. Now, we move the magnet so that the magnetic field strikes the atom, supplying energy which forces an electron to leave its atom and become a free electron. The result is a sort of electron chain reaction. In a substance such as a length of wire, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. Now, in studying electricity, we're mainly interested in the movement of free electrons. So, for convenience, we'll look only at the action of electrons in the wire. When the magnetic field sweeps down across the wire, electrons move in one direction. When the magnetic field sweeps up across the wire, the electrons move in the opposite direction. This movement of electrons in either direction constitutes an electric current flow. If we move the magnetic field more slowly across the wire, fewer electrons are affected in a given period of time, and the electric current flow is decreased. And when we stop moving the magnetic field, the electric current flow stops, and the electrons again move in all directions. If this wire is connected to a meter, we find there is no electric current flow. When the magnetic field is moved down, this meter shows current flow in one direction. If the magnetic field is moved up, the meter shows current flow in the opposite direction. We can change the amount of electric current flow in several ways. Move the magnet faster, more current flows. Use a stronger magnetic field, still more current flows. Now coil the wire so that several turns are in the path of the field. Again, the current flow is increased. Stop moving the magnet, current flow stops.